Hello everyone. For this tutorial video, I'd like to explain how to use integrals to find the area under a parametric curve using the substitution rule. If we recall from Calculus 1, the substitution rule is used to integrate composition functions, which we have here because x is a function of t now rather than simply one input. So if we have y as x as our input, we now have a composite function rather than a single function, because of the fact we define x as a function of a third variable rather than one variable. This means that change in x over change in t is simply the derivative of x with respect to t. So we multiply both sides by change in t to get change in x by itself, which remember we did for the substitution rule in Calc 1. This means we are now integrating y of x of t times the derivative of x with respect to t. And we must also pay attention to changing the limits of integration from x's to t's. So instead of using the normal a to b, we would use different symbols, alpha to beta, in order to distinguish the fact that we are integrating with respect to a different variable than simply x, because of the fact x is a function of another variable now. In conclusion, this is our final answer for the area under a parametric curve. For example, if we are given this parametric set, where the angle is the parameter rather than t, and told to limit the parameter between 0 and 2 pi, we would first see the derivative of x with respect to angle as 6 times 1 minus cosine of angle by simple derivative rules. So we plug this in, as well as change of y over change of x, which interestingly enough is the same thing. So we have 36 times 1 minus cosine of angle, 1 minus cosine of angle is squared, with respect to change in angle. And we integrate from 0 to 2 pi, as those are the limits of the parameter given. We factor out the 36 and expand the squared. We rewrite cosine squared with the trig identity. We also rewrite the 1 as 3 halves. We now integrate using simple antiderivatives. Compute the antiderivative at 2 pi minus the antiderivative at 0, and get 108 pi as our exact area. Now that we have figured out how to compute areas under parametric curves, we can discuss how to figure out arc lengths of parametric curves next, using similar formulas to arc lengths we derived for y equals function of x. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.